In the Bohr model, we start with a central nucleus of charge positive Ze. An electron of mass m and charge dE moves in a stable circular orbit around it with a constant tangential velocity of v. For the electron to maintain a stable orbit, the inward electrostatic attraction from the nucleus must exactly equal the outward centripetal force required for circular motion. According to Coulomb's law, the electrostatic force is calculated as 1 over 4 pi epsilon naught, multiplied by the nuclear charge Ze times the electron charge e, divided by the radius squared. The centripetal force required to keep the electron in its path is defined by the mass of the electron times its velocity squared, divided by the radius of the orbit. Bohr's key insight was that angular momentum is quantized. It can only exist in integer multiples of Planck's constant divided by 2 pi, where n represents the specific orbit level. To find the radius, we first rearrange the quantization formula to solve for velocity of v. This gives us an expression involving n, h, m, and r that we can substitute back into our force equation. We substitute our value for v into the force balance equation. This creates a complex expression where we square the quantization terms, which will eventually allow us to isolate r. The final derivation shows that the radius of the nth orbit is epsilon naught times n squared times h squared, divided by pi mze squared. This proves that the radius increases with the square of the orbit number. For a hydrogen atom where Z equals 1, the smallest orbit, the ground state, results in a value known as the Bohr radius, which is approximately 0.529 angstroms. In summary, Bohr's model explains that electron orbits are quantized and their distance from the nucleus grows quadratically as the principal quantum number increases. This concludes our derivation. Generated by Vision Solve AI.